Today's topic is pushover analysis with RM bridge. First, we'll present an overview of seismic design methods and pushover analysis. Then we will have a demo example run in RM bridge, and at the end we'll have an Q&A session. Seismic design. There are two commonly used seismic design methods: force-based design and displacement-based design. For example, H$RFD bridge design specification address the force-based design, whereas the H2 guide specification for RFD seismic bridge design cover the displacement-based design. In the force-based design, there are three methods depending on the structural complexity: importance of the structure, distance to earthquake source, ground condition, etc. Equivalent static analysis, which includes uniform load method and single mode method, as categorized by H$RFD bridge design specifications. This method is suitable for regular bridges that respond principally in their fundamental mode of vibration. Response spectrum analysis or multimode for bridges in which coupling of several modes in orthogonal direction can take place. Nonlinear time history analysis is used for important complex structures in poor ground condition and close to an active fault. The second common method, in fact, this is becoming much more common now, is displacement-based design using nonlinear static pushover analysis. Seismic analysis method, force-based design. H$RFD provides guidelines for deciding which force-based design method should be used. The decision is based on whether the structure is regular or irregular and the seismic zone indicating the severity of the seismic run motion. Equivalent static analysis. In equivalent static analysis method, the structure is idealized as single mass spring oscillator. Cross-sectional dimensions and equivalent stiffness are estimated. All permanent load is lumped in a single vibration mass. Typically inertial effects of live load are ignored. Classical methods are used to calculate the period of the fundamental mode of vibration. Design response spectrum is then used to calculate the elastic seismic coefficient and the resulting seismic force. The seismic force is then reduced using the force reduction or response modification factor to account for intended ductile behavior of the structure. The bridge is then analyzed and designed for this design seismic force. Response spectrum analysis. The response spectrum analysis method is similar to the single mode method, except in this case a linear elastic dynamic analysis is performed to calculate the various mode shapes and their mass participation factors. This method is used when coupling of several modes in the orthogonal direction is possible and for long, highly skewed and curved bridges. The designed seismic force is calculated by combining the contribution from the various mode shapes using either the CQC or SRS methods. Nonlinear time history analysis. The nonlinear time history analysis method is used for critical, important, and complex structures. Structures close to the active earthquake faults, when the second order effects are expected to be very large, and when base isolation devices providing large damping are installed. This is a complex and time-consuming analysis. Typically, several site-specific time histories needs to be analyzed. Displacement-based design. In recent years, there has been a trend away from force-based procedures to those that are displacement-based, wherein a bridge is designed to have an adequate displacement capacity to accommodate earthquake demands. Displacement-based procedures are believed to more reliably identify the limit states that cause damage leading to collapse, and in some cases produce more efficient design against collapse. In this design philosophy, bridges have low probability of collapse but may suffer significant damage such as cracking, reinforcement yielding, concrete spalling, etc. The controlled damage with resultant softening of the structure significantly reduces the seismic force, as can be seen in this figure. The main objective is to make sure that the deformation capacity of a structure exceeds the deformation demand. Deformation capacity calculation. As discussed earlier, the structure is expected to undergo significant damage at the maximum expected displacement. The amount of displacement that can be sustained or the displacement capacity of the structures need to be calculated. The displacement capacity may be limited by excessive plastic hinge rotation, footing settlements or uplift, total lateral displacement, or a structure instability due to formation of too many hinges. The displacement capacity calculation should consider nonlinear material models, concrete confinement, cracking, spalling, and crushing, reinforcement yielding, strain hardening, second order effects, large and small p delta effect, axial load flexure interaction. Deformation demand calculation. The deformation demand can be calculated using the equivalent static analysis method or the equivalent dynamic analysis method. Both of these methods are similar to the single mode and multi-mode analysis methods reviewed under the force-based methods. The only difference is that here spectral displacement rather than spectral acceleration are calculated using the design response spectrum. Nonlinear static pushover analysis. Pushover analysis is an approximate alternative to nonlinear time history dynamic analysis. As discussed earlier, the time history method is complex, tedious, and time-consuming. Pushover analysis, on the other hand, involves fewer calculations. Pushover analysis also uses a single response spectrum as opposed to a suite of ground motions. Pushover analysis identifies limit states that cause damage leading to collapse. The method is thus quite suitable for structural design. The main weakness of pushover analysis is that it uses static analysis to capture dynamic effects and as such may be inaccurate. There are several pushover analysis methods in use. All of them, however, have the same overall steps but different details. They are all driven by the same strategy of providing deformation capacity larger than demand. Pushover analysis in RM bridge. Pushover analysis implementation in RM bridge includes rigorous deformation capacity calculation. It offers three methods of calculating the displacement demand, namely FEMA 440 displacement modification method, FEMA 440 equivalent linearization method, Eurocode 8 N2 method. There are nonlinear static procedures which convert multi-degree of freedom models to equivalent single degree of freedom models and use response spectra as opposed to ground motion records to estimate global displacement demand. The typical method of computing the performance point where capacity equals demand is illustrated for the Eurocode 8 and 2 method. Here an ADRS curve, acceleration, displacement, response spectrum curve, instead of the conventional acceleration versus time period curve is used. The actual capacity curve in black is converted to an idealized capacity curve in purple. The elastic response spectrum in green is reduced to inelastic spectrum in turquoise. The performance point is denoted by PP. Deformation capacity. The deformation capacity can be calculated by displacement control method or force control method. At each load or displacement increment, new estimate of tangential stiffness based on the previous deformation state is used, which is basically the Newton-Raphson method in convergence. The reinforcement yielding is tracked at all levels throughout the structure, accounting for distributed plasticity. A concentrated plasticity approach typically followed in the US of assign a specific location of plastic hinges at top and bottom of columns are not being directly implemented in RM bridge. However, it can be approximated with the help of zero length spring elements. FEMA 440 equivalent linearization method. The equivalent linearization method is based on the assumption that the maximum total displacement of a single degree of freedom system can be estimated by the elastic response of an oscillator with a larger period and damping than the original. The method utilizes estimate, ductility, effective period, and effective damping. In step 1, the maximum total displacement is estimated by linear approximation of the capacity curve is developed. In step 2, the effective stiffness, effective period, and effective damping ratio are calculated using the empirical formulas. In step 3, which you can see in the picture, spectral acceleration SA is calculated using the response spectrum. In the step 4, the spectral acceleration SA is used to calculate the lateral force and associated lateral displacement, delta. In step 5, the displacement calculated in step 4 is compared with the assumed displacement from step 1. The above steps are iterated until the convergence is reached. 440 method is called displacement modification method or also called coefficient method. In this method, the total maximum displacement is estimated by multiplying the elastic response by one or more coefficients. The coefficients are typically derived empirically from series of nonlinear response history analysis. The 5 steps procedures is similar to the equivalent linearization method. The main difference is that this method uses a single spectrum with 5% damping. Eurocode 8 N2 method. Finally, in Eurocode 8 N2 method, the response spectrum is the conventional format of spectral acceleration versus period is converted into ADRS format. This conversion accounts the inelastic behavior through the use of empirical ductility factors. Similarly, the idealized force displacement curve is also converted to ADRS formats using the transformation shown above. The intersection of the capacity curve and inelastic spectrum designates the performance point where the displacement capacity equals the displacement demand. Now we'll have a demo, an example how to perform pushover analysis in RM Bridge. Pushover analysis in RM Bridge demo. Here's a bridge example that we are using in our demo. It's a 3-span bridge. The total length is 140 meter. It's a curved bridge as you see in the plan view of the axis of the bridge. It has 3 spans. The first span is 40 meter, second span is 60, and the last span is 40 meter. The height of pier is 20 meter, and this picture on the bottom left hand side shows the profile of the bridge. For the material and cross section of the bridge, we have a box girder which is 13 meter wide, and the depth is varied between 3.5 to 5 meter. The material that we use in this example is concrete C45 megapascal, and for reinforcement we use a steel grade 60. We use the nonlinear material in this example, and if user wants to define the user-defined property, it's possible in RM Bridge, and for example he can define the user-defined material such as Mander model. For the pier cross section, we have it as a rectangular, 1.5 meter by 5 meter, and the total reinforcement that we use in the pier is 1.6%. Pushover analysis in RM Bridge. For capacity curve, we need to create load cases for the dead loads and load case for the lateral load case that we during the analysis increase step by step. And also we need to define our diagrams in RM sets, which we define them in RM sets. The diagram is for base shear displacement, and in this diagram we track the displacement, which is we consider at the mid-span. For the demand curve, we need to define our response spectra first. Then we need to perform eigenanalysis. To perform eigenanalysis, we need to create a load case as a mass, and then we need to set up our parameters for the demand calculation, which will define them in the RM set. And we will perform 3 different methods. So we'll set up the parameter for these 3 methods, which is Eurocode N2, Eurocode 8 N2 method, FEMA 440 displacement modification, and FEMA 440 equivalent linearization. And the last step before we run the model, we'll set up the parameter to consider the nonlinear geometry or P delta effects and basically nonlinear material as well. So in summary, these are the steps that we use to perform pushover analysis on bridge. First, we create a load cases for pushover analysis and eigen analysis. Then we define our response spectra. After that, we create our diagrams and set up the parameters in RM sets. Then we create actions for eigen and pushover analysis, and then we run the model. Now we go to the RM. Here's the model that we are using. Basically, I imported this model that already defined in RM Bridge. First step, we need to define the load cases for this model. For the load cases, we have load cases as a mass for the eigen analysis, for the self weight, and then superimpose dead load. And also we have the load case for the pushover. It contains self weight, superimpose dead load, and one load case for pushover in Z direction. Z direction is shown here. It's in this direction, perpendicular to the bridge. And this load case for the pushover, we set it up to incremental increase during the analysis. In the next step, we need to define our response spectra. We have predefined response spectra in RMBridge for different codes that you can find them here under extra. For this example, because we want to compare three different methods together, we use this response spectrum for Eurocode that you can see it here. Here are the values. These are the spectra for Eurocode 8. In next step, we need to set up our parameters for pushover diagrams and set up the parameter for the demand set for pushover in Z direction. Here we have the two options, diagram and then pushover. Diagram, we will set up the parameters for the capacity curve. Here we define the shear base versus displacement. For the x-axis, we use the displacement that you see here. We use node number 118, basically at the middle of the bridge here. And the component we select here is the displacement. For the vertical axis, we use the base shear, total base shear in all the reactions that we have in the bridge. So we use them here. First, we choose the capacity name here. Then we have this option for phi function. This option will use if user wants to use the user-defined modal shape. First, he need to define it under the variable, and after that, select it here. Then we have the control node 118 at the middle of the bridge. Direction is in Z direction. And then for the Eurocode N2 method, we need to define our transition period, TC. Basically, we'll set it up from the response spectra that we imported from Eurocode. For the FEMA 440 displacement modification, we need to set up the transition period. Again, we use it from the response spectra that we imported. Lambda factor that we have here is the factor between 0 and 1. We use this factor to calculate the target displacement. This factor is used in C3. The recommended value is 0.5, but user has an option to change it. The site class, user need to select the site class. We have different site class here, A, B, C, D, E, F. Site class is used to calculate the parameter, the factor C1. And we have an option here. This factor C0, C1, C2 is automatically calculated by the program, but user has an option to override these parameters here. In this example, we set it as a default that this parameter calculated by the program. In the FEMA 440 equivalent linearization, we need to set up the damping factor. We'll use it from our response spectra. Hysteretic type, we have different options, general, bilinear stiffness, and strength degrading. We select it as a general. During the analysis program, select the appropriate one. And for the procedure, for FEMA 440 equivalent linearization, we offer two different procedures. Procedure A, basically, which is direct iteration, and procedure B is the intersection with multi-acceleration displacement response spectrum, MADRS. In this example, we select procedure. The next step is to set up the actions that are required to perform the analysis, pushover analysis. So we go to the schedule actions. First, we need to perform the eigenanalysis. To do that, we need to define the number of the modes that we want to calculate. In this example, we select 10. And then we need to, in the input 2, we need to define and use our reference load case that we defined earlier. We select it here. And then we create another action for the pushover analysis. This action, as you see here, it has pushover and pushover D. Pushover, we have in this action, we will calculate the capacity curve with this action pushover, and pushover D action basically referring to calculating the demand. And because we are performing three different methods, I have created three different pushover D, one for the Eurocode, the other one for the FEMA 440 equivalent linearization, and the last one is for FEMA 440 displacement modification. Now, for the pushover, as I said, to calculate the capacity curve, we need to set up these parameters. First, we need to use our load, reference load case that we created earlier. We select it here. Then the modal file from the eigenanalysis. We use the modal file here. And then we need to select the mode that we want to use in the analysis. As I said earlier, we can have the mode number here or use the phi function. If you remember in the RM set diagram, I said that user can have a user-defined mode shape, so he can select it here. For the mode, why I select mode number 2, because we know that usually mode number 1 is the dominant mode. But if you look at the output from the eigenanalysis, you see that in the z direction we have the highest participation in the mode number 2. Because of this, we choose mode number 2 to calculate the capacity. Then we set up how many steps we want to perform for the pushover, number of the steps, and then number of the subsets that to converge the result we selected as 5. Type of increment for the what type of increment that we want to use. We have two options in RM: force increment or displacement. In this example, we use the displacement. And the last input that we have is input number 3. We select the pushover diagram that we define in RM set, and also for material nonlinear analysis, we want to use the nonlinear material in the analysis here, and then we select the name as an output. Now for the demand curve, I explained one of these actions because they are the same, just the procedure is different. Pushover D, as I said, is for calculating the demand. First, we need to, in input 1, we select the reference load case that we created before here. Then in the procedure, basically we select the Eurocode. In the other two, we select FEMA equivalent linearization and FEMA 440 displacement modification. For input 2, we select the response spectra, and then type of response spectra, we provide two options. One of them is a spectra. User has an ability to use the time series if he doesn't want to use an X spectra and he wants to use the real-time history, a real time series, he can use it here. And input 3 is referring to the RM set. So from the RM set that we defined, we select the RM set here. After this, we need to recalc or run the model. Before running the model, as I said, we need to consider the effect of P delta for nonlinear analysis. So here we select nonlinear analysis, P delta effects. And now we run the model. We had 4 pushover actions. We will get 4 diagrams. The first one is the capacity curve. This one is upside down because the values are negative. And for the demand, we have 3 demand curve as you see here. One of them is for the Eurocode. The other one is for the FEMA 440 equivalent linearization, and the other one is FEMA 440 displacement modification. Let's look at a diagram for the Eurocode. As we explained earlier, in Eurocode N2 method capacity curve, the red diagram that you see here, we transform it to ADRS format, then find the find the bilinear approximation of the capacity curve, the orange line that you see here. The next step, we will use the 5% elastic response spectra in the ADRS format. After that, we will transform this 5% spectra to the inelastic response spectra that you see in the black line here. And the intersect between the inelastic response spectra and bilinear capacity curve give us the performance point. Performance point is is written here. It shows that the structural displacement is 0.34, 2 meter, and the base shear is 25,000 kilonewton. As you see, after the performance point, and that shows that our bridge has enough capacity. For the FEMA 440 equivalent linearization method, first we convert the capacity curve into ADRS format, spectral acceleration versus spectral displacement that you see in the red line. Then bilinear approximation of the capacity curve calculated, the orange line that you see. After that, 5% elastic response spectrum converted to ADRS format, the blue line. Then parameter T0, T effective, and beta effective is calculated by the program. And then based on the procedure B that we selected, multi-acceleration displacement response spectrum, as you see in the black curve, calculated, and the intersect between this black curve here, MADRS, with the bilinear approximation of the capacity curve, give us the performance point. And again, as you see here, after the performance point, still we have more capacity in the structure. That shows that our bridge has enough capacity. And information about the performance point is shown here for this method. The structural displacement is 0.308 and base shear is 24,000 kilonewton. Now let's look at the result for the FEMA 440 displacement modification. As I said, in this method, we use the base shear versus displacement. The capacity curve is the red one shown here, and then program calculate the bilinear approximation and intersect between the two, give us the performance point. The information about performance point is here. The structural displacement is 0.317 meter and base shear is 24,312. And as you see, again, after the performance point, still our structure has more capacity. Detailed information about these methods can be found as an XLS output. Here, for example, for FEMA 440 equivalent linearization, if we open this Excel file, you can see the detailed output, information about the method, capacity demand calculation, information about the procedure, and then iteration. Now here, if you look at the comparison between the results in this graph here, here is the capacity curve, base shear versus displacement, the blue line, and the output result for the EC8N2 method is here, it's shown here. For the FEMA 440 equivalent linearization is the square one, and triangular one, the red one, is FEMA 440 displacement modification method. You see that because we use the same response spectra, we expect to have the close value. As you see here, the capacity is more than the demand. This concludes the presentation. of the demo. Now we go and have the Q&A session.